All right. So, a couple of things before we get going. You guys got kind of lucky on Tuesday. I had to end up leaving, to take my wife to the hospital. So, just as a kind of point moving forward, make sure you're keeping an eye on Canvas announcements. I'm trying to plan and schedule as much as I possibly can, but in the next month, 6 weeks, some unexpected things might pop up. So just keep an eye out for Canvas for announcements. I'll try to use that to kind of convey any information to you outside of class. But for you guys, should be good to go. You didn't miss any class on Tuesday, so it didn't impact you. I think, we talked a little bit about last class, kind of where we're at. We really are just going to be rehashing kind of the materials we've been talking about last week and this week today, just seeing more examples. Next week, I'll start kind of going back probably to early, like material from early in the semester. So we're kind of doing more like exam review, kind of preparing us for that exam, which should be on that October the 17th in class. All right. So I will try to get here a little bit early that day, so we can kind of get started right on time. I've got the other section of this 371 right afterwards. So it's kind of a hard, fast date or time to be due. I have to turn the exam in right at 11 o'clock. Okay. So I'll try to get here so we can kind of get started pretty early. I'll get that practice exam up later this afternoon. I told you I'd probably get it up yesterday. Given what happened Tuesday and some of the chaos in my life, I didn't quite get everything up in the timeline that I had. But that problem set and kind of the quiz 3 are up there. I kind of said Tuesday I'd hold off maybe until after today's class to think about even taking quiz 3 because we're really going to be rehashing more examples that'll help you with that. I'm also aware on problems. I think it's for this section, and I got a reply from Canvas. I'll try to fix it this afternoon. I might just have to end up doing it manually. It's showing problem set 3 is 0 for everybody. I know I have the exact same settings for both my sections, and one of the sections it shows is missing, and one it's showing for is 0. So I got a reply from the Canvas people, our IT people. I don't really necessarily love it because I don't think they're kind of just dismissing that it's happening, and I'm ignoring what I'm telling them. But regardless, I'll get that switched so that it doesn't look like a 0 and it's not impacting your grade on Canvas. The very worst, I can manually go in and just change everyone's to missing until that due date passes, right? So the due date on that problem set, I have that set to be due before we start class on that Tuesday before the exam. I probably wouldn't hold off that long to work on it. I try to get that problem set out of the way because we want to start studying for the exam really next week, all right? So I'll get that practice exam up later today. You'll have that problem set, that third quiz. The quiz is going to be due by the end of the day next Friday, right? So trying to kind of get you to get that done a little bit sooner, give you a little bit more time for the problem set because I realize kind of state is not second nature to us still, and kind of give you a little bit more time to work on that. Okay. So that's kind of where we're at before we jump into material. Is there anything else I wanted to mention? Any questions for me, logistics or anything about kind of timelines before we jump into material here today? Also, do you guys like sitting in like this? I mean, it's not a right or wrong answer. Do you guys like sitting with a desk like this? Or would you rather have them be kind of more like this? See, no one's choosing these. Maybe it's because it's up front. You guys don't really care. No preference? Are you guys alive? Right? No one cares? No preference? This is okay?
I don't really care, just set up like this.
You just sit here because it's set up like this? I don't necessarily love it, but if you guys ever have any problems with it, I can kind of send an email to the maintenance and tell them, like, I don't know who's using this room before us, but like every night, kind of, I'm sure we're the first class that's in here. So maybe I'll have them try to make it so it's a little bit more like a normal classroom. But you guys don't really care. I don't necessarily really care. I just figured I'd ask. So let's jump into material here. So we really went through all the slides last class, and really just additional work is kind of where we're at. So I'm going to pull up this do file, that MLR inference, and we had started to look at it last class, but I just want to work through some more examples. So I'm going to scroll down here. I think we looked at a lot of this. What do I want? I want it. There we go. Class 2 work, right? So here I think I've got this powerlifting data set. So let's see, did I put it as, so I actually saved it as a .dta for you guys. So I'm just going to open that up to make sure it's the exact same file. So we'll go to open, we'll have it dragged on our OneDrive, open up that powerlifting data set. So I don't remember when I found this, but I found this data set and it's got a bunch of different meets, powerlifting meets. So if you don't know anything about powerlifting, it's fine. We'll kind of talk through it. There's, it's just people lifting weights, right? That's all we need. We need to think about it as, right? So I've got this data set kind of opened up and here, just kind of good practice. Now that I have it saved as a .dta file for all of you guys, I don't have to kind of import it as an Excel file. So I'm just going to copy and paste that code so I have it to reuse if I want to reopen the data set. So the first thing I'm going to do is kind of generate this category just to kind of review. If I want to create dummy variables, so there's different powerlifting, like they can use different equipment, right? So one of the ones is kind of, they call it kind of multiply, right? So this is like they're using these crazy powerful things. I want to identify whether or not this meet was a multiply meet. It will be a multiply meet if the other two types of meets are equal to 0, right? So I'm just going to generate this 1, 0 variable. We don't have to worry too much about that. We'll kind of talk through that once I use that later on. What we're going to start out with is this naive regression, right? So let's say I run this regression where this Y variable just represents the total amount that these people were lifting, right? And I think it's in kilograms. And then body weight was the individual's body weight in kilograms. So before we run this regression, what do we think that the slope coefficient estimate likely is? The amount of weight that a 100-pound person can lift versus a 300-pound person, what do you think happens? It increases. So we probably think that slope coefficient is positive, right? So we can run this regression, and sure enough, right, I find this kind of positive slope coefficient. Can I say that body weight has a statistically significant impact on predicting the total amount of weight lifted? What would I look at there? P-value, right? We want to know, is the p-value less than our threshold alphas, 0.1, 0.05, 0.01? It's basically 0, so it's less than all of those. We can say that it's highly statistically significant, or we can reject the null that it has no effect. We found strong evidence that it has an effect. Okay? Now, if I left off, say, the standard error test statistic, let's say I put like a white box over this, how could I use, what else could I use how do I use my confidence intervals to make a rejection decision? As long as that confidence interval doesn't include what value, I know 0, right? And we're starting out assuming that slope coefficient is equal to 0. The confidence interval is telling us the true slope coefficient is somewhere in this range. So if that range doesn't include 0, I know I actually would be rejecting the null, right? Now I can only do that at the 95% level here. I think I mentioned last class, a couple of you Googled and found a way. Let's see if I can remember what it is off the top of my head, this syntax. I think it's, you can add this level onto the end and then specify. So I can do like the 99% confidence interval. But when I run this regression once, I make my rejection decision using the confidence intervals, I can only do it at one level, right? Whatever level it's being reported to. If I wanted to do it at multiple levels, I'd have to run this regression multiple times, specifying different levels of confidence intervals that I want it to show me. In fact, I could actually even do, I don't have to do the conventional ones. I could do like 85. I can now say, can I reject the null at 85% level? Okay? But we can use those confidence intervals as long as it doesn't include 0. We know we'd be rejecting the null. Okay. So how would we interpret this slope coefficient? So remember, these are all in kilograms. So what would a 1 unit increase in our X variable be? The individual is 1 kilogram heavier. We would predict the total amount of weight they lifted would go up by 5.2 kilograms. Okay? So it's just a 1 unit change in our X variable, causes our predicted Y variable to go up by whatever our slope coefficient is. Okay. Now, I have this regression. Let's see, yeah, this marker might be dead. So yeah. Let's make sure. So we've got kind of total kilograms that they're lifting. Got our intercept, got our slope coefficient, and we had body weight in kilograms. Okay. So this was kind of how we were going to make, this is the regression we were running. We're going to see some estimates for our intercept and our slope coefficient. We saw it there in the state output. So if I think about this slope coefficient estimate between body weight and total weight lifted, it's going to contain the true effect, right? But also we said some bias, right? If I run these very naive regressions, I haven't controlled for a lot of other factors. All of those are going to bias my estimates. So what will that bias be? What would be whatever the effect of beta 2, or sorry, this variable I left out would have been, right? Beta 2. So maybe let's think about the important omitted variable. Let's say I left out this variable of whether or not the individual is identified as male. So this would be, if I had included male into my regression, what would have the effect been? Right? And then that multiplied by the covariance between the variable that I included, here I'm just going to abbreviate that using BW, body weight, and then the variable that I omitted from my regression. That gets divided by the variance of the variable that we included, right? So we included body weight here. So in general form, we kind of think about this as covariance of the variable we included, the variable we left out, variance of the variable we included. Okay. So I actually have this variable, so I can eliminate that bias by doing what? Simply, so if I'm running this regression, how do I eliminate the bias that comes from this omitted variable? I just add it into my regression, right? Then, as soon as I add it into my regression, it's like my interpretation becomes holding all else constant, so holding that variable constant. Now what's the effect of 1 more kilogram of body weight, right? So as soon as I include that regression, I completely eliminate that bias. We can think about what this bias would be and then kind of look at the data and actually prove this to ourselves. So if I do include that dummy variable of male, what do you think is true about the sign of that slope coefficient? You don't have to be politically correct here. Do you think males are going to predict? Yeah, you probably think that it's increasing the total amount lifted, right? So you think this is probably a positive value. What about the covariance between male and body weight? Well, males on average are heavier, right? Taller, larger, so we would have a positive covariance. Right? Now, the variance is always going to be positive, so the estimate I see is going to be a little bit too high, right? There's a positive bias, so the value I see, right, that difference between the actual effect and the slope coefficient I see is going to have this positive bias. I like this example because I think these are hopefully, easy. There's no discussion about what those signs would be. Okay, so let's go see kind of what the actual data looks like. There we go. So if I instead just run this regression where I've now included that male coefficient, what should be true about the coefficient that I see on body weight? Once I include male, it should go up or down. So if the bias we had was positive, yeah, that's going to be removed. We're actually see a lower coefficient value. Sure enough, if I run this, I see that it's a little bit smaller. Right? Now, how would I make my interpretation on that male variable? If the individual was male relative to the 0 group, relative to not being identified as male in this data set, the predicted increase in the total weight lifted would be 196 or about 197 kilograms more. Okay. Yeah.
So it's a dummy variable, and it's like male. Would that be like, that wouldn't be like the least amount that a male can lift out, because that would also be factored in with the body weight, right?
Yeah, essentially, it's like saying holding constant the body weight. So you're looking at 2 individuals with the exact same body weight. What's the predicted difference between kind of like, you can think about it this way, the average male weight lifted and the average female weight lifted, right? Being in that one group, being identified as male relative to non-male, what's the predicted increase in that Y variable?
Okay.
So it's kind of telling
That's
you.
what I meant, but I just said it really.
That's all right. Yeah, so it's kind of telling you, essentially, when you include these dummy variables, this is good to kind of revisit a lot of this. So if I'm thinking about that relationship between body weight and total weight lifted, right? It's kind of like what I'm doing is I'm saying there's some intercept, and the line of best fit for the female group there's going to be some relationship between total weight lifted and body weight. What that male identifier does, it says, look, we know this relationship exists between body weight and total weight lifted, but for males, their starting point is going to be a little bit higher. How much higher? It was like 196 or 197. So it's almost like we're estimating two lines, like there's best fit lines, but for the one group, that line is going to be shifted upward.
And it's parallel between the whole, everything else constant.
We're assuming that this relationship between body weight and total kilograms lifted right now is the same for both the 0 and the 1 group. So it's the same for males as it is for females. We know maybe in likelihood it might not be. We are not going to talk about before this exam how we identify differences in slope. So for right now, we are just identifying what that slope is, that relationship between body weight and total kilograms lifted. But we can estimate different lines in terms of shifts, right? So the relationship's still the same, the slope's still the same. But for that one group, we know that it's going to be a little bit higher, right? So we're kind of allowing for shifts in this line of best fit, but not changes in its slope. Questions on this before you? Yeah.
So when you generate, it's on the data, but when you generate the regression, what's the difference between the male group and
Yeah, so I can think about what does that constant represent? That would be when all of the x variables are equal to 0. So it gets kind of weird, right? But to have that visual, the intercept interpretation would be when all of the x variables are equal to 0. So when the individual is not male and their body weight is 0, what would the predicted weight lifted be, right? Now, we can make these predictions with the intercept. We know that we never see anybody with a body weight of 0, right? But that's still how we would interpret it, right? We know that the actual data, we might not see anybody show up until we get to, I don't know, whatever the lowest kilogram weight is in the data set. Any other questions on this? Okay.
They're crazy numbers of their kilograms.
So it's not one lift, just to get into the, this is the sum of 3 different lifts. Yeah, so yeah, it makes a little more sense if you know that. Sorry, it's the total weight across 3 different movements, right? So it's large amounts, but we're also not controlling for a lot of other factors. There's likely bias in these coefficients. So for instance, let's think now about that male coefficient. If I look at that, I'm like, oh, I'm maybe this like, sexist, but she's, oh, males are so much stronger, right? Well, let's hold off because let's think about this for a second. If we had, well, it's already got it now, so let me see if I can get it over here. So let's say I run this regression that we just did with male included. That coefficient estimate is going to contain the true estimate, but it might also have some bias. Now, it's not going to have a bias related to the body weight because we've included that in our regression. But what's something else that might be different about men and women that is going to be kind of correlated with how well you can perform? Could be age, but the one I would probably think about, at least I might know a little bit too much about this powerlifting stuff, but so my brother's an exercise physiologist. So really all that is, like when you're thinking about moving things, it's all about angles, geometry, right? So height matters a lot when you're doing different movements, throwing a ball, all these other things. So I haven't put height in here. So let's say if I had included the individual's height, right? What do I think the effect of height would have been times the covariance of whatever variable I'm excluding, which was height, and the variable I'm interested in the coefficient of, which was this male variable, and then divided by the variance of the variable I included, which was male in my regression. Right? So if I did include height in my regression, this one is maybe not quite as clear. Probably decreasing, right? The taller you are, the angles at which your body moves are not as actually desirable. Seems kind of weird, but you look at exercise physiology, published papers, that's what they find. So I think, so I'm doing this, I'm kind of ad-libbing here. So I think it's negative. We'll end up, we can actually determine whether or not it is. What's the covariance between being considered male versus non-male in height? We know that one's probably positive. On average, males tend to be tall. And then variance is always positive. So we know the estimate we're seeing actually is underreporting the effect of being male. Right? Now, we can see if that's true, right? Maybe this is positive, but we can kind of check that since we have the data. So if I instead run this regression, but I now also include, and I can't remember what it's called. Oh, do I not have height? I thought height was in here. Oh, I could use age. I wanted to do height. I know that I had it originally in here, and I must have dropped it for the one that I gave you guys. Well, we talked through one. I guess we'll have to use a different variable to kind of prove it to ourselves. But let's say, what's another one we could do? We could do age. So let's say, there it gets a little bit trickier. And when I'm thinking about what the sign is. So what probably ends up being true in this data set if I had to imagine. So now instead of height, let's think about we're including age, because I guess I remembered incorrectly that I don't have height in this data set. It tends to be that 40, 50 years ago, what do you think was probably true about the prevalence of females in these powerlifting meets? More or less, right? So when you're looking at the current data, you might see some of these like 50, 60-year-old men in there, but you don't see near as many 50 and 60-year-old women. So that covariance between male and age, right? If the individual is male, it's likely on average, we see a higher age value. Now, what would the effective age be on weight lifted? Probably negative, right? When you're 30, you do a lot more than when you're 50 or 60, right? So we probably have a negative bias there. So we can use age just like we were going to use height. So if I run this regression, if I think that I had a negative bias before, well, once I include age, I'll eliminate that. So my estimate on male should actually go up. Sure enough, if I run this regression, I can kind of see, oh, actually, it's counterintuitive to what I thought, right? So here, now the effective male is actually a little bit lower, right? So it must have been, I got one of these signs incorrect.
Or the majority of the data set is like 18, 19, 20.
It could be, right? So it might be that relationship between male and age, maybe that is negative. Like maybe there's just really young individuals in this data set. And so my thought experiment, my intuition kind of failed. Now, when it comes to like the exam or something like that, if I'm asking you to put like a sign to this bias, as long as you explain to me the intuition behind why you believe the covariance between these two variables is what it is, and why if you included that variable, what its effect would be on the y variable, as long as you kind of justify that, I'll kind of grade it accordingly. Right? But when we have the actual data, we can kind of see this play out. Okay? One thing that you had to do in the other problem set, so kind of going back to this body weight male example where we left out male as the omitted variable, we said that we could use this correlate command. So body weight and male, and I want the covariance, right? So here, I'm going to have let's get rid of this because we don't need this anymore. Run the naive regression, run the regression where we included male. So what we see here is the actual effect of being male was 196. That would be our kind of beta 2. If we use this correlate command, we can also get the covariance of that variable I included, the variable I left out. We kind of cross values, or the diagonals tell us the variance of these two. So I can get the variance of body weight, the covariance between body weight and male, and the actual effect of being male. So what am I going to do there? I'm going to use Excel to be my calculator. So let's put a view, zoom in a little bit here so you can see what I'm doing. So we said the size of that bias was just going to be the coefficient on the variable I originally excluded. So remember, we originally excluded male. So this is what? 196.93. Multiplied by the covariance between the variable I included and the variable I didn't. So that would be 5.46. And then divide that by the variance of the variable I included in my naive regression, which was just body weight. So 524.4. And I see that bias was about 2.05. Now I can kind of verify this by, well, what was the original coefficient I found? It was 5.2 approximately. What was the coefficient after I included that important omitted variable of male. It was 3.15 about. Sure enough, that was the size of the bias, right? Now, I sometimes can't do this to myself if I don't have the important omitted variable in my data set, kind of like with height, right? I can't verify that because I don't have that in my data set.
Okay, that's kind of what I was gonna ask, is why would you ever?
Yeah, why would you ever not include it, right? Why would you ever just, if you have the variable, why would you not include it into your regression? That's
And there's the, reason for you use the correlate covariance, which you just.
because I can just compare the two. Yep. But if it was something that I didn't know, right, I really can't ever figure out what beta 2 is, that missing coefficient. So all I can do is really put a sign to it. But I'm just kind of using data to prove to you that that formula would hold. Yep. So in practice, what you might do, if I don't have this variable in the data set, another researcher with another data set might tell me, oh, I have a different powerlifting data set. Here's what beta 2 would have been. Here was what the covariance would have been. I can kind of then adjust my findings accordingly. Yeah.
How do you find the bias out again?
Yeah, so we said it was just going to be the coefficient of the variable that I originally excluded or omitted times the covariance of that omitted variable and the variable that I included in my original regression divided by the variance of the original variable. And that was kind of the numbers I was entering into Excel there. I was just grabbing that from the state output. So this was what? Kind of following along. 197 approximately. This was 5.46, and this was 524. Yeah. Okay.
So the second value is the covariance between the two.
This, yes.
Like, I'm saying that in this data, not anything wrong with it is.
So the covariance is going to be, yep, male body weight. That's the covariance of male body weight. The diagonals just tell you the variance. It's kind of weird, like the covariance of something with itself ends up being just a variance. Any other questions on this? I know we're kind of going back to an old topic, but it's all kind of with this multiple linear regression stuff that we've done. Okay. All right. So the next thing we'll do is more like what we were talking about last class. So let's say I now have this regression. I know I don't want to omit this important variable of male. I've also included kind of this raw, which kind of identifies that they're using like no assistive or assisting equipment. So just a 1-0 variable there, kind of controlling for whether or not they're having equipment that helps them lift more weight. And then we're including age as well. So maybe I say, okay, did this added variable of age and kind of whether or not it was raw, or is that jointly significant? So compared to when I was just running the regression with body weight and male, is adding in these two additional variables, is it allowing me, we know that if I add in more variables, what's going to happen to my R squared? It will always go up. If I add more variables, I can always explain a little bit more of the variation. But can I say that the amount of variation I'm explaining is statistically significant or has went up at a statistically significant level? So I know the difference between my R squareds when I add in more variables will always be larger. But is the difference between my old R squared and my new R squared, is that statistically significant? Is that difference statistically significant? So we said last class, and it's harder to see, but I'll kind of try to give you an idea of what we're doing here. With this joint significant test, so when we were just doing a test for one variable, we said, how do we calculate a test statistic? It's just our coefficient estimate divided by the standard error on that slope coefficient, right? So that was coming from a student t distribution. We're still going to be calculating a test statistic when we're testing for joint significance. But it's kind of like now what we are really curious about is the R squared from our unrestricted model where we've included all of our variables, is the difference between that and the restricted R squared, is this statistically significant? Well, we only have sample data, so we can only use the R squares that we see from our regressions. So it's almost like we have sample R squares. So the statistic that we're now interested in is the difference between those sample R squareds. So now it's still going to be a test statistic, but we said we know it's always going to be positive. We're only looking at the right tail. So it's going to be coming from an F distribution or a F test statistic. So how are we calculating that? Well, just like before, we take the sample coefficient. Well, we're not dealing with coefficients now. We want the sample difference. So we're going to take the difference between our restricted and unrestricted R squared. Now, kind of behind the scenes here, the way we calculated this, there was like an n-2. We go all the way back to sample means. So we had like an n-1 in the variance calculation. So we have some similar things going on here. We're actually going to divide this difference by the number of variables we want to test the joint significance of. Okay. Then what's in our denominator? 1 minus the R squared. Let me think if this is of the, I have to look it up. I believe this is, it's the unrestricted, right? Okay. I didn't want to put it down wrong. And then we have n minus k minus 1. Okay? So you can kind of see here, like we're dividing by n-2, n-1. This is kind of like the standard error or the standard deviation of our difference in R squareds. It's not quite that, but you can kind of start to see the similarities when we're calculating these test statistics. So this is going to be how we calculate that. Well, we can get this from Stata, right? So here I had 2 variables I was including. So my Q is the number of variables I want to test the joint significance of. So this was a 2. The number of variables I included in my unrestricted model. So there I had body weight, male, age, and whether or not they were lifting without equipment, that kind of raw dummy variable. So this would be 4. Then I'm going to have to get my R squareds and my sample size from Stata. All right. So I look here. All right, I'm going to run this regression. Well, I'm going to run both of these, right? Here's my restricted model. I'm leaving out 2 variables. Here's my unrestricted model. It's got the 2 variables I want to test the joint significance of. I'm going to run both of these. So I can see my R squared went from 0.65 to about 0.69, right? So adding in these 2 variables did increase my R squared, but can I say that it increased them at a statistically significant level? So I'm going to take these 2 values of 0.6939 and 0.6539. I'm going to plug them in. Maybe I can get this thing to switch over. There we go. So this one was what? 0.6939. And from the other one, it was 0.6539. Yeah. Unrestricted 0.6939. My sample size, we'll go back, was something, where is it at? So this is a really large data set. So 86,380 observations. Huh? So you know that if you have your 2 R squareds, which one always has to be smaller? The one that you didn't include as many variables in, that's your restricted model. That's the one that only had 2 variables. The one where you included 4 variables, your unrestricted model, that's going to have a higher R squared. So if we're looking at that output, right, our restricted model, where we only included male and body weight, has a lower R squared than when we have male, body weight, and age and raw here. Okay, so then it's just a matter of getting those values plugged into our calculator, calculate what that F statistic is, or we can kind of, I used Excel to do my, I used Stata to do my math here, just plugging all those values in. I generated this new variable I called fstat, and then I just looked at the output of it. You could do this in a calculator. Oops, why didn't it like that? I don't know, but it summed it, right? Oh, because I have should have put this down as a comment. I just wanted to sum that. So I generated it and then just wanted to report to you kind of what that mean value was. It ends up being what, 5,643. Okay. This is an insane test statistic, right? So why is this test statistic, this F statistic, so large? Well, I'm going to revisit something else we talked about. So I'll put this over here. Maybe. Why does this keep? There we go. So let's think about the equation that we have for this F statistic. we had a sample size that was 86,000, right? So if my sample size goes up here, what's happening to this fraction? My denominator is getting larger, so this fraction in the denominator will be getting smaller. If I divide by a smaller value, what's happening to this fraction? So my F statistic is going to be really large. When I have these really high sample sizes, it's going to make my F statistic really large, which means what? My p-value is going to be lower, and it makes it more likely I can reject the null. What was the null here? That these added variables didn't have any predictive power, right? That there was no joint significance. So if we can get these really large sample sizes, quite often we're going to find joint significance of adding in these additional variables, right? Which is nice because now we have some statistically significant support and we're getting more explanatory variables in there, hopefully making better predictions.
Just to kind of get an idea of R squared, so. If you included every single variable that was present in your data set, would R squared be 1?
So
Or like 0.9?
if you had, it'll get closer and closer to 1. In theory, what you would need to have an R squared of 1 is you would have to have every single variable, every single type of thing you could measure that is impacting your dependent variable. Will you ever have every single factor? Probably not, right? So to have an R squared of 1, that's our goal, right? We like to see R squared close to 1, but in practice, I mean, we can get it up into the 90% range, we're doing pretty good. You know, because even if we're trying to predict things like wage and we've got education, age, the field you're working at, there's a lot of intangibles we're never going to have data on.
So R squared is not relative to your data set then, right? So my question, I guess, is even if you include everything in your data set, your R squared won't be. So R squared is not calculated from 0 to 1 based on your data set entirely.
So it'll be based on your data, the variation that exists in that Y variable that you're trying to predict, how much of that variation you can explain using all of the variables in your data set that you've included. So it is based off of your data set in the sense of you're giving the R squared is a proportion of variation you can explain with all of your right-hand side variables of the total variation that exists in that variable you're trying to predict.
Right, but an R squared of 1 is not based on using all of your variables.
No. Okay. You could use all the variables in your data set and you can end up with an R squared of 0.01 if they're not variables that matter that much. Yeah. Any other questions on this? You know, one more thing I want to kind of prove with this example. So we'll also go back and revisit our adjusted R squared for a second. So our adjusted R squared was going to be 1 minus what? The proportion of variation we can't explain. So this was like portion of our variation unexplained. And then we multiplied that by a factor, which was n minus 1 over n minus k minus 1. So k here, once again, the number of variables we're including in our regression. So as my sample size gets larger, it's kind of hard, you know, you can kind of envision this. So let's say, this is a weird one, but let's say I had a sample size of 3. I'm only including one variable, right? So 3 minus 1 would be 2. 3 minus 1 would be 1. I'd have this scaling factor of 2. Well, what if I have 10? Well, then it becomes 9 over 10 minus 1 over 8. Notice my value is going to be a lot closer to 1. So as I increase my sample size here, this factor is getting closer and closer to 1. If I had a really large sample size, it's going to be approximately 1. You can imagine, like with my example, I've got 86,000 observations. I included 4 variables. It's like 86,000 divided by 85,995. It's going to be really close to 1. So what's going to happen is that's not going to change what I'm subtracting, this proportion of variation I can't explain by very much. The actual R squared is just this. So as this is getting closer to 1, my adjusted R squared is going to be more and more similar to or closer to my actual R squared. In fact, with a sample size of 86,000, what do I notice about my R squared values here to the fourth decimal? Exactly the same. I can't even tell a difference out to the fourth decimal. Now they are still technically different. If I went out far enough, there is going to be a decimal where the adjusted R squared starts to be lower, but out to the fourth decimal with these large sample sizes, it doesn't really matter, right? Okay. Any questions on that? We'll keep moving. Okay. All right. So get our F statistic. Oh, the command we could use instead of calculating this by hand, and something I might show you the data output of and have you use. So let's say I run this regression, I then run this test command. Hopefully it gives me the same test statistic that we just calculated by hand. So it'll kind of test the joint significance of those two variables that I asked to test the joint significance of. It gives me the F statistic and the p-value. So now with a p-value here, at what levels could I say that these two variables were jointly significant? Well, the p-value of 0, I can reject that they have no significance, right? That they're both equal to 0 at every single level. Yep. Now, if I look at that F statistic, why is it a little bit different than what we calculated up here? So 5,643, 5,637. Well, I kind of put it in the code here, but we're using 4 decimals. This test command uses the actual value of that R squared that's stored behind the scenes in Stata. So it's just getting a little bit more accurate. And when we're dealing with like, you know, things that are very similar to like very small numbers, this can cause quite a bit of a difference, you know. I mean, it's not that much difference, right? If we're talking about percentages, 5,640 something and 5,637, that's not that crazy. But it will be slightly different because Stata can use the actual R squared. All we can use is kind of that 4th decimal that we see reported, if we're doing it by hand. Any questions on that? Okay. Do I want to do this here? I've already talked through it. Let me think if there's anything down here that I think is more important. Yeah, there's more examples. So we'll do this. I think it's worth kind of taking the time. So we just ran all these regressions with 86,000 observations. So what I'm going to do here is generate a random number, and it's going to, you know, I'm going to select only the lowest 100. So this is randomly sampling 100 observations from this data set, and I'm going to call those observations small sample, right? So hopefully if I use the tab or sum command, sure enough, 100 of the observations have a 1, the remaining ones have a 0. So I can now use this conditional statement to only use this smaller sample. Now, would you want to do this in practice? No, I'm just doing this to prove to you what happens when we have smaller data sets, right? Because these concepts are important in terms of why we want these larger sample sizes. So let's say I run that exact same regression that we did above, but I want to do it for kind of only that small sample size, right? So I'm going to hit enter here. Now, the first thing I'm going to want to point out, well, let me run these back to back so I don't have to keep scrolling up. So I'm going to run the regression with the full sample, run the regression just for that small sample of 100. So 100 observations versus 86,000. Right? Well, we just talked about when I have a higher sample size, what happened to the difference between the adjusted and R squared and R squared? They became pretty much the same thing. So as I have a smaller sample size, what's going to happen to that difference between the two? It's going to be larger. Sure enough, if I run my regression with a smaller sample size, now there actually is a difference, right? To the second decimal, there's a difference between my R squared and adjusted R squared. Right? When I have this smaller sample size, we'll also notice what happens to the statistical significance of each individual slope coefficient. Okay? So we don't typically look at it in this way, but in the calculation of that standard error, there is an n-2 in how it's being calculated. Right? There's like the sum of some, don't worry about this. We won't touch on that. So if my sample size is becoming smaller, what's happening to this fraction? Dividing by a smaller number, it should be going up. If my denominator is now higher, what's happening to my test statistic? It's going down, which means my p-value will be what? Smaller test statistic. P-value will be, you guys can't answer this, the exam might not go well. Smaller test statistic. Yeah, I'm going to have a higher p-value, meaning it's going to be less likely I can reject the null. So when I'm comparing these sample sizes, right? Notice the test statistics here for all of my variables, 176, 229. Or sorry, yeah, I'm putting it the right ones. They kind of become much smaller, 5.7, 6.2. In fact, some of these variables like age and raw really, which were highly statistically significant before, from a smaller sample size at our kind of conventional levels, I can't really say age has any statistically significant impact on the total weight level here, right? That p-value is 0.28. So these smaller sample sizes, it's always going to be harder to reject the null. That's also going to be the same thing will also be true about our F statistic, right? So if I come down here now, oh, actually, I don't know if I can do this. We'll see if this works. Oh, I went too high. There we go. I want to test, already had it in there, test these two variables. Right? So notice before, our F statistic before, that test statistic, the difference between R squared, it was like, what, 500 and something? What is it now? It's only 2.3, right? So having these smaller sample sizes are also going to make not only the test statistic of every single individual slope coefficient smaller, they will also decrease, right, that F statistic of my joint significance tests. Right? So here, now, can I say that age and raw, these two included variables, had any additional predictive power or that they increased my R squared at a statistically significant level? Not quite. Doesn't quite make it past any of my thresholds, 0.105. So smaller sample sizes are always going to lead to smaller test statistics, larger p-values, less likely we can reject the null. That applies to each individual slope coefficient, but also these joint significance tests. Okay. Any questions on that idea before we keep moving? Okay. Here I just wanted to kind of revisit this. So these three variables here, if I wanted to run this regression, so there's only 3 types of meets in this data set. So this raw, that's where they couldn't have any assisting equipment. Wraps, they could have some moderate equipment, and then multiply was like this most extreme. So there's only ever those 3 types of meets. So if I try to run this regression, these are going to be direct linear functions of each other. Anytime it's a raw meet, the other 2 would be 0. Anytime it's a meet where there was wraps, raw and multiply are 0, right? Same multiply, these other 2 are 0. So if I try to run this regression, what is Stata going to do? It's going to kick one of them out, right? Now, it doesn't really matter which one gets kicked out here. Although we said in practice, what's probably a good one to leave out is going to be either the highest or the lowest group, right? Because then our slope coefficient estimates become a little bit more intuitive. So think about here, if we leave out these multiply meets where they're having the most assistive equipment, well, we would expect the other 2 categories, the weight lifted would be lower, right? Or we have negative coefficients. Now, if I didn't rerun this regression, how could I tell the difference in the predicted weight lifted for a meet that allows wraps relative to a meet that allowed nothing? So without rerunning this regression, how could I tell the difference between the predicted weight lifted in these meets that allow these wraps versus meets that allow nothing, or these raw meets? Yeah. Simply finding the difference between their coefficients. Yep. So there's about what, 4, right? 4.6. Okay. So I don't have to rerun these regressions every single time I want to compare these different categories. When I have these categorical dummy variables, I can just compare the coefficients of the 2 groups I want to find the difference between. Okay. All right. What else do I have down here? Oh, I think I already mentioned this earlier, but we'll kind of look at it, another one. So let's say I've got this smaller sample, and let's say I left off the test statistics, the p-values, the standard errors. Okay? how could I determine which of these variables I could reject the null hypothesis for that the slope coefficient is equal to 0? What columns could I look at? So if I don't have the p-value, I can't do hypothesis testing. I can look at so let's say I don't have the test statistic. The other thing that we can use is what's all the way on the right-hand side? Confidence intervals, right? So I know that if my confidence interval, it's telling me with 95% confidence, the true value of this coefficient is in this range. So for body weight, the true value of that coefficient is somewhere between 2.7 and 5.1. So can the slope coefficient be 0? So I know that if I were to run a hypothesis test at a 95% level, I would be rejecting that that slope coefficient is equal to 0. What about the next one? 111 to 215. 0 is not in that range, so I know I'll be rejecting. What about the next one? Negative 3.1 to 0.79. 0 is in that range, so 0 could be one of the true possible values for that slope coefficient, so I can't reject the null there. And then looks like the other two don't include 0, so I can reject the null for those as well. So I might kind of give you some output like on the exam or maybe even the third quiz, where I don't give you the test statistic or the p-value, and you have to make decisions based off that confidence interval. Now, this is a little tricky. Actually, I wouldn't do that. So I won't even try to confuse you there. So let's say instead of confidence intervals though, let's say I did leave out the test statistic and the p-value. How could I use my coefficient, my standard error to determine statistical significance? So if I have my coefficient, my standard error, what can I calculate? I might have misspoke. If I have my slope coefficient and my standard error, what can I calculate? My test statistic, right? So we said earlier, that's simply going to be take the slope coefficient divided by my standard error. So I could reproduce that entire column of test statistics, right? Once I have those, and this is where when we go back to review some of the earlier stuff, we'll kind of revisit some of this. But even at a sample size of 100, we really said anything over 100, instead of using the student t, we can actually use the approximate values from the standard normal. So what were the 3 values for our kind of two-tailed test from that standard normal distribution? So it was going to be positive and negative 1.65 would have been our critical values for an alpha of 0.1. Okay. Our rejection region would be any area more extreme than that. We then had what? Negative 1.96 and 1.96. Those were our critical values for an alpha of 0.05. And then we had final one, I think it's 2.58. That's our critical value associated with an alpha of 0.01. So if I had those 3 critical values, right, I can reproduce my test statistics, and then it's just a matter of plotting those test statistics. So let's say I didn't have this column, but I go through, calculate, just take the coefficient divided by the standard error, and I come up with each one of these. If I were to plot them, so let's think about plotting 6.41, and then we'll think about plotting this one, negative 1.18. So for that body weight slope coefficient of 6.41, where would that be? Way out here, what levels can I reject that body weight slope coefficient at? So I reject if that test statistic, whatever it was, 6.41, sorry. It's more extreme than every one of my critical values, so I can reject at every single significance level. What about the test statistic that I had on age, which was about negative 1.18? Well, it is not more extreme than any of my critical values, so I'd actually be failing to reject at every level. So I could recreate those test statistics, use my critical value approach to determine what levels I could reject at. Now, I probably wouldn't ask you to do it for every single variable. I would just ask you to do it for one, but this would be kind of the procedure that you would use, okay? Any questions on that before I keep moving. Okay. All right. Kind of already talked about this. Where are we at in time? We got a little bit extra time. We kind of already went through this example with age earlier. Do you guys have any, do you have any general kind of questions about anything that we've talked about kind of over the last, what, two and a half weeks with multiple linear regression or anything that we've covered today that you're kind of like, could you go back to that? You have questions over that? We're feeling okay. Yeah.
You just go back to how we thought about determining the signs for covariance and variance in the bias.
So let's do one. Let's do a different data set here. Let's do, oh, I think I've got to set my global. Use this data. And I'm going to just start a new one. So math score. Well, I can use this. So let me copy this over. Fix that. So I'm going to think about, see what variables I have here to make a good example. I know there's a test in here. Let me see. Grade, status, magnet. I think if I remember right, hopefully this is this ends up playing out. So I've got my math score. I'll include a couple of these variables, and then so these magnet schools here. Let's see if my memory is correct. Yeah, we'll run with it. So there's supposed to be, oh, maybe it's not magnet. What are the other types in here? I think the charter schools here might be a better example. Why didn't it like that? Oh, I need to use charter school. Okay. All right. Let's make sure that this is what I think it is. Okay, we can run with it. So let's say I've got a couple variables here, and I'm looking at that slope coefficient on charter school. Right? But I think that, you know, who goes to charter schools typically are going to be individuals whose parents probably have what? More money. So let's see. I think there's an income variable in here. No. Is there a college variable? Oh. Hold on. Oh, this is the one. Sorry. Let's open up this data set. This one might help. There we go. I think this is what I want. So I want to get a good example. So let me see. Rental income here. Well, we can run it anyways. All right, so I'm going to run this regression instead, where I'm predicting GPAs. Oh, what did I forget to do? Rename some variables here. There we go. So I'm going to try to predict college GPAs using these kind of variables here. So if I'm thinking about high school GPAs, right? So I'm going to think about that slope coefficient. So I found here that it's positive and very highly significant. But when I'm getting that estimate, I'm getting the true effect plus some bias, right? So let's say I have some information about whether or not the parents went to college, right? And we'll think about if I omitted that important variable, what would the effect of that variable have been? So kind of think about here instead of 2, maybe parental college, right? Times the covariance of the variable I included, which was high school GPA, and then kind of whether the parents went to college here. I then would divide that by the variance of the variable I included, which was high school GPAs. So if I had included parental college, so this was just a 1 if the parents went to college, 0 if not, what do you think is maybe true about kids whose parents went to college, their first year in college, do you think they would perform better or worse? Probably better, right? If nothing else, just having someone to ask questions about neither of my parents went to a large university, so going somewhere with tens of thousands of students was a culture shock, right? If they had, let's say my kid, right, is probably going to be around this campus quite a bit, it's going to feel like nothing, right? It's not going to feel as big, right? Or just knowing how to navigate a large university, it's likely that effect would have been positive. Now, having parents that went to college, what do you think is likely going to be true about their kids' high school GPAs? You could maybe tell me a story where they're more rebellious, so they have lower GPAs. But I think in general, if we look at like the trends, and also there's just some genetics involved that more intelligent people on average tend to have more intelligent children, or even if it's not intelligence, ambition, right? Going to college. So we think that if your parents went to college, what's probably true about your high school GPA, by taking school a little bit more seriously, this would probably be a positive value as well. So the estimate we see is actually going to have this positive bias baked into it. So although it looks like high school GPA is a really strong predictor of college GPAs, it probably is, but maybe not as strong as we saw, because it's picking up part of the impact of having parents who went to college. So we go back and let's see, do I have the parent college variable? Do I need to create it here? So college. So yeah, so we'll do mother, college dad is equal to 1, or so if either one of their parents went to college, right? We're going to create this 1, 0 variable. I'm then going to run that same regression, but I want to eliminate that bias. So I'm going to include that important omitted variable, which was, did either of their parents go to college? So if we thought that the bias was positive, the estimate we were seeing is too high, once I run this regression, my new slope coefficient on high school GPA should be lower, right? Because I'm eliminating that positive bias. So I'm going to run that regression. Sure enough, compared to before, so I had 0.0925. Well, it's a little bit lower, 0.92. So there was some bias, but it must not have been that large, right? I would have thought that would have been larger, but we never know until we actually run these regressions. So that's gonna, the type of example that I think about, being able to put a sign to that bias. On the problem set, I might ask you to determine what it is. You would compare those coefficients between the two. On the exam, like on a quiz, I'm probably going to ask you more about, can you put a sign to the bias, right? Or based off of some output, where maybe I give you the covariance, you can see what the coefficient of is just of the variable that we were omitting. Maybe you have to kind of calculate the size that way. But in practice, you generally just include the variable if you think that it's important. Right? Is that what you're asking?
Yeah, exactly.
Okay.
That makes sense.
Sorry, it took me a little bit to come up with one on the fly there. So before we get out of here today, I want to work through some stuff. So everybody who's here, oh, no, that's not what I want to do. I'm going to, I think I have this all set to go. So I'm going to publish this. I'm going to add it to the home page so we can kind of work through this together. Everyone should get all the points who are here, and I have a way of making sure people that aren't here don't get any of the points. So if you want to start this quiz now, it should be up on Canvas. So is it showing up to you guys? Okay. So we'll kind of work through these problems, right? So this first one, if I'm thinking about, I've got one thing we didn't touch on today was imperfect collinearity. So just as kind of a reminder, we talked about perfect collinearity, and if we have that problem, it's not a big deal because Stata will use this default and toss one of those variables out. But let's say I have something like tax per pack and cost per pack, and I'm looking at a cigarette use data set. Well, inherently, when I have a higher tax, what's that going to do to the cost? It's going to increase it, right? They're going to be a linear, they're going to be a function of each other. So I know I've got some imperfect multicollinearity that's going on. So if I'm thinking about which of the following are going to be true, we said, what happens when I have imperfect multicollinearity? So if I have imperfect multicollinearity, if we go back, we said the reason why we're concerned with this is because it's going to do what to one of my variable standard errors? Increase it. If I'm increasing my standard error, what's happening to my test statistic? I'm dividing by a larger value, so it's going to be going down. So we didn't walk through the like mathematical proof, but if you have imperfect multicollinearity, because one thing is a function of the other, your standard errors calculation on at least one of the variables will be too high. Right? In fact, we actually worked through an example where sometimes it only impacts, excuse me, the standard errors of one of your variables, but sometimes it'll impact the standard errors of both. So the answer here really should be the standard error on cost per pack and or tax per pack will be larger. So at worst, or sorry, at best, it increases the standard errors of one of the variables. At worst, sometimes it'll impact the standard errors of both.
So it's because, like you said, one is a function of the other, so what are those pencils?
In the other one.
Total cost is a function of tax per pack. If tax per pack has error, then that error is going to be magnified in the
other one. You can think of it that way. Yep. So we know that at least one, but possibly both. So and or, right? Both of these could be affected. So hopefully everyone's going to get this one correct here. Right. Question 2. If I wanted to test joint significance here, what would the value of my F statistic be? So how would we calculate this F statistic? All right. We go back to the equation. The thing that we're really looking for is the difference between our R squared from the unrestricted model and the R squared from the restricted model. So here I've got my restricted model up here, unrestricted model down here. So what? 0.8994 was my R squared from the unrestricted model. 0.8973 was the R squared from my restricted model. I then, and you'll have these formulas. In fact, the formula sheet's up on Canvas. I can show it to you before we get out of here today. We will divide that by the number of variables that we kind of left out of the restricted model. So here I had population income. Here I've got population income, unemployment rate, metro, vaccinated. So I've included 3 additional variables in that unrestricted model. So Q is going to be 3 there. I don't like to worry about parentheses. So that's my numerator. So what's my denominator? Well, that was going to be 1 minus the R squared of the unrestricted model. So 0.8994. We then divided that by our sample size, which was 100 here, minus the number of variables we included in the unrestricted model, which for us would be what? Yeah, 1, 2, 3, 4, 5, minus 1. Right? Now I've got my numerator, my denominator. I'm just kind of doing this in steps. I should get an F statistic rounded to the second decimal of 0.65. Okay? So hopefully everyone's getting that F statistic correct. All right. Yep, just 0.65 there. Like on the, well, if I was to ask you this, like on the quiz, I would tell you round your final answer to the second decimal. Generally, it'll be the second decimal. For some things, I might say third or fourth. If it matters, more often than not, it's going to be the second decimal. Yep. Assume that instead of 100 from our previous example, where we were what? Estimating number of COVID cases based off of these different variables. Let's say I had not 100, but I had 3,000 counties. Which of the following is not going to be true? So if we have a larger sample size, what's that going to do to all of our test statistics? Increase them, right? So our F statistic will likely be large. That's true, right? We also said if our test statistics are larger, the p-values are going to be smaller, right? So if I'm thinking about here, we're more likely to reject the null for a single hypothesis test of any coefficient. Well, if my p-values are smaller, I will be more likely. So that one's true, right? The coefficient estimates will be larger. What did we say? Anything about the coefficient estimates? No. No, right? It's only impacting sample size is only impacting statistical significance, right? Or measures of like our adjusted R squared. So for that third one, we said if n is gonna be larger, what happens to the gap between R squared and our adjusted R squared? Well, in the one regression we had, it completely went away. To the fourth decimal, they looked exactly the same. So that gap there is gonna increase. That actually shouldn't be true. Right? So the ones that aren't true, this was supposed to be set as a circle, all that apply, is the gap is actually not going to increase, but it would decrease, right? So that one's not true. And then the coefficient estimates will be larger. That one's not necessarily true either. So if you answered either one of these, I'll kind of go in on the back end and answer is correct. This was supposed to be a multiple answer question. I must have accidentally hit the wrong type. I think is only letting you select one. Yeah. So as long as you select either one of those, I'll go back in and kind of give you credit for getting that correct. In fact, I'm not really that concerned if you get the correct answer that we just worked through on any of these. I mean, I want you to know what the correct answer is in terms of your responses, because I don't want people to be doing this not in class. Today's number, let's go with, 73.14, right? So that way, the only people I know were in class today is if you put 73.14 in, make sure you submit this quiz before you leave. I'm going to close it out as soon as everyone says that they've got it kind of entered in. And that way, even if you got one of the other ones wrong, I set this last question to be 10 points. So I doubt anyone's going to guess, what did I say, 72.13? I doubt. Well, don't worry. I'll change it on the back end. So anytime I use these, I can always go back and change the number. So I have to continuously change the numbers, right? So before I set it up, I just put in some random value there and then I change it as I use them. Yep. So don't worry about it. Like I said, I'll go back in and kind of make sure it's regraded, but 72, now I'm already blank. 73.14 should be that number you put in there. I'll make sure I get that kind of changed once I get back to my office. Yeah, that's fine. Really either one, right? It was either that the coefficient estimates will be larger. That's not necessarily true, but also the gap between our R squared and adjusted R squared should be right going down or decreasing. Say it again. Yeah, the way it's set up now. I'll go in and change it so that you can see both of them. Yep. All right. We got that number written down so I don't forget it. I'll get those changed this afternoon. Other than that, any questions? I'm going to have some additional office hours. I'll post an announcement up later today. Should be 1 to 4 tomorrow. Have a fun, safe weekend. I'll see you guys on Tuesday. All right.